Okay, so sorry, we continue basically from here. So we have reference coordinate which is pxpy 12.9 and 2.5. So the idea that I want to bring the end effector position to that point. Okay, so the question is, what is, we need to do the inverse, and we want to get the set of theta 1 and theta 2 options that can bring me to that, basically can bring the robot arm to that position. So we have this set of equation, basically, sorry, set of theta 1 and theta 2 combinations. We have 30, 60, 30 minus 60, minus 8 plus 60, minus 8 minus 60. So if we basically draw them like this, where this is the xy, and these are the four combinations that we got basically. And now the first thing that I can use to actually, let's say, ignore or refuse some of the solutions is to look at the robot arm itself and see the limits of the degree of freedom. For example, like your shoulder as a human, you cannot it has basically the rotation is not 30, 60 degrees, 360 degree, because there is a limit to rotation for each joint. So mainly the joint, they have 90 degree actually working space. Some would have 180, but for example to have 360 degree, some they do have for the shoulder part sometimes, but basically it's also not that common. So they have limit, and you need to look at this for example, and you need to check, okay, which case would actually looking at the robot arm, looking at the physical constraints of robot arm, which of these basically cases can be considered. And here we are saying that only 7B, and basically, so this is B and C, so it's basically that can be considered. And this is the rest basically cannot be achieved, as I say, due to the complexity of the robot arm. So you could have two solutions here. Now again, would depend in this case on the shortest path. For example, if the robot arm originally was, I don't know, here, then I would take this solution more than this solution, because this one's closer than doing that full rotation. And so it depends on the shortest path. It depends on the collision of avoidance. Let's say if the movement of robot arm to reach this let's say configuration would mean that, for example, this robot arm would collide with an object, and if it chooses the other one, it won't collide, and basically you can use that one. So this is how we can actually select the option, select the solution out of set of solutions. Now this is the algebraic method. Of course, the advantages, as I talked about also in the first session, that algebraic methods are accurate, quite accurate, if you get the equations. So because the solution is very precise. Now there are other ways that basically can be considered. They are not accurate but less complicated. They are more flexible to be used for basically any robot arm. For example, if you have really robot arms with high degrees of freedom, like 9 or more, with very complicated structure, then it's really hard to find these equations, and sometimes you cannot maybe find solutions. So this is why there are other solutions or the other algorithms like the numerical optimization methods. Now the idea is there that it's an optimization method. We have the target position of the robot arm that I want to reach, and I have basically the forward kinematic model. This forward kinematic is a function of the theta, and of course, and as an output with that is the position. So as an optimization, I have always the objective function or the cost function, which is basically here, which is the difference between the target position and the output of the forward kinematic, which is the actual position. And the goal, of course, is to find the optimum theta or set of thetas that basically would reduce that cost and eventually bring it to zero. Now for numerical optimization, there are different methods, for example, genetic algorithms, there are particle swarms optimizations, and other basically numerical optimization methods. There are many that can be used for this regard. Now the drawbacks there is that it's relatively slow, so it's much slower. So for the algebraic method, if you find a solution, you don't need to search for it anymore because you find it. But in this case, you need to do it always. So always we are doing numerical optimization to find the optimum thetas. Now they of course need high computational power. If you're using swarm optimization, you need to have like maybe parallel pools to do the or cores to do the computations. And it has local minima problem as any optimization issue or problem. For example, you might don't converge at your target solution, but basically minima problem or minima solution, like not a global, that is the best. Now we have the black box you can consider methods, which is basically here the most famous one is using neural network or artificial neural network. I don't know if you have been or if you will be in the machine learning lab or lab and lectures. I give lecture in summer. So this basically the main topic would be there is about neural network and or deep learning. And this is basically an example here where you can use black box models or machine learning models to solve such a problem. Now, black box models or machine learning models, they use training data, and the idea that I have basically a model with many parameters like the neural network model, and what I want to achieve is basically I want to optimize these parameters in a way that I can always predict the accurate, let's say, joint angles given the target orientation and position of the end effector. So to train such a model, you need training data. You need really rich training data with a lot of examples. We have basically corresponding, let's say, samples or rows where I have the end effector position and the corresponding joint angles. Now, theoretically, I can do that easily because I have the forward kinematic model. And if I have forward kinematic model, what I can do is I actually now change theta 1, theta 2, theta 3. So let's say I define the range of theta 1 between, I don't know, 0 and 180, theta 2 between 0 and 90, theta 3 between 0 and 90 with a step size 0.1. Then I do this movement of the three combinations. So I am changing the position of robot arm using the three ranges. And when I'm doing that, I can always calculate the position of the end effector using the forward kinematic. And then I can store this data. Now I can do the inverse, basically by training neural network to take the positions as an input and the joint angles as an output. And I train this network, and if, for example, it fits well, and if I train it well, where I need to do what is called bias variance trade-off, where I basically need to do cross-validation to check if this network is generalizing well, which means by generalizing is that if I have now some input data that is not or actually didn't exist in the training data, so it's basically called out of sample or unseen samples. Just example given is that, let's say if I have if I have a training set where x is equal 0, or if I have a training set I have a point where x equals 0, y equal 1. Okay, then I have this, also I have of course the theta 1, theta 2, theta 3, and therefore have this basically theta there. Now if I have also another point in the training set where I have, let's say, x equal 1 and y equal 2. So these are training point. Now if I come now with this, let's say this is my training set, and now I come with an unseen example, which means that was not considered in the training. And this unseen example, let's say it is x equals 0.5 and y equal 0, for example, 0.5. Now if you remember, x had values 0 and 1 but never had 0.5 in the training set. Now this case it's interpolation, because actually 0.5 is between 0 and 1. So the network, yeah, could generalize, because neural network are not bad in interpolation, but they are bad in extrapolation, which means for y, I trained with 1 and 2. I never trained with 0.5 or 0. So 0.5 actually is extrapolation here, not interpolation, because we never trained with two, let's say, variables or two values where 0.5 lies in. So this extrapolation when your network is less accurate when it comes to extrapolation. Now, in addition to that, the complexity of having big data, that you need big data, training neural network is computationally also expensive, especially if the network is large. But basically the main disadvantage is if you don't have enough data, if you don't consider really well training of this network, you may end up with instability due to overfitting or other issues, which means you could, for example, have an input, then you get really unpredicted output and unstable output. Let's say that would move the robot arm from position dramatically to another position that may be far and in a very fast movement. Then this would be unstable and it might cause some damage. Now, as I said, this is a big topic, just the new machine learning. If you are interested, or I don't know if you have visited one of them, the courses, then maybe you would understand what I'm talking about. If not, in some other the lecture where we cover this deeper. Now, the next method, which is called the Jacobian method mainly, and this is also very common beside the algebraic. So the most common, actually, we have the algebraic and we have the Jacobian. And so far we have been analyzing the position of robot without considering its velocity and acceleration, or mainly the inverse without considering the velocity acceleration. But actually velocity and acceleration are important to the dynamic analysis of trajectory of a robot arm, and they actually can make the inverse kinematic quite an easier task. So what we see here is that if let's say I'm taking the forward kinematic model, which is a function of q1, q2, q3, which is basically representing, let's say, theta 1, theta 2, d3. So q is kind of generalization of the control parameters, which could be theta or could be d, for example, and they are called q here. So the speed actually, or the change of the forward kinematic with respect to t, or the velocity, is of course here is different. So basically a set of partial differential equations. So you're actually saying that it is a change of so first of all, basically it's the change of f with respect to delta t, and what we are doing here, the chain basically trick. So what we are saying is that it is basically the change of f with respect to q1, because q1 changes itself over time. So we have f over q1 multiplied by q1 over dt, which is basically this would vanish, of course. Then here we have f q2 multiplied by q2 dt, and here basically plus f q3 multiplied by q3 dt. Now, what we are seeing here, let's say that we have rotations only. Then q1, q2, q3 are rotational. That means they are theta 1, theta 2, and theta 3. Now, the delta, or basically this basically d theta 1 over dt is the angular velocity, right? That's why they are replaced here with omega 1, omega 2, or omega 3. And they are the angular velocities of the joints. Joints means actuators. Actuators, we know the velocity of them always. So theta 1, theta 2, and theta 3 are known. And what we have here is basically that now the change of the forward kinematic model with respect to change of theta 1. And this is a change of the forward kinematic with respect to change of theta 2. And this is with respect to theta 3. So giving the forward kinematic model, which is basically q to 0 to n of q, if I take now the dx over dt is equal to dx over dq and multiply by dq over dt, which is what we have done before in the previous slide. What is here basically happening is that what we did here, we just now take this into matrix multiplication form. What we see now here is on the left side is a change of the position of the end effector over time is equal to the Jacobian matrix, which is this one, a set of the partial differential equations, multiplied by the change of the rotations, for example, or if there is displacement, then it's also linear change, which basically represent either the angular velocity or linear velocity in this case. And this is basically Jacobian matrix. Now, basically the number of rows of Jacobian matrix equals 3 usually, or probably sometimes more, but basically the most cases is 3 that represent the 3 changes or the 3 coordinates basically, which is x, y, and z of the end effector. I said it could be more because it could be we have also the rotation of these coordinates. But here let's say we have x, y, z, which means that we have 3, and the number of columns basically is equal to the number of control parameters, or actually to the degree of freedom of robot arm. If I have 5 degrees of freedom, then I would have here 5 columns for Jacobian matrix. If I have 4, then it will be 4 columns. So let's take an example here and see how we can use Jacobian to get the inverse kinematics. So we have the same simple 2D planar or 2D manipulator, and here we have the L1, L2 as the dimensions of these 2 links, and these are the coordinates, and we have theta 1, theta 2. Now this is the forward kinematic model, a very simplified one, where we have the end effector position of x and the effector position along y, and here we have it's equal to L1 multiplied by cosine theta 1 plus L2 multiplied by cosine theta 1 plus theta 2, and this is basically for the y coordinate. Now what I want to do is to get the Jacobian matrix by now taking the speed or velocity equation by taking basically the differentiation of that and that over time. So we do as we did before. We take here x over delta theta 1, then theta 1 over t, and so on. Then basically this would represent the angular velocities, right? And this would represent, or this basically they represent the Jacobian matrix. So in this case, that means this part and this part are the Jacobian. And what we are doing here is, okay, this is basically the differentiation of that equation over theta 1. So we differentiate this equation with respect to theta 1, and we get basically this term, this one here. This one represents the differentiation of basically x with respect to theta 2. This differentiation y to theta 1 and y to theta 2, which represent the second row here. Okay, and this is my Jacobian matrix. Now how can I use the Jacobian matrix to do the inverse kinematic? Now the inverse Jacobian model basically is that what we have done here is that we took that the position or the velocity of position is equal to the Jacobian matrix multiplied by the angular velocity, or let's say here the control parameters change over time. Now what we want to do is the inverse, which means that now we need to take the theta or the change of the control parameters over time, which we can adopt, we can change, as I said, is equal to the inverse of the inverse matrix. So now we have one matrix that we can inverse in this case, and basically this is the inverse of Jacobian matrix, which is multiplied by the change of x basically, or of the x here. If dx is relatively small, so basically if dx is relatively small, then we have we have basically the change of x is equal to xt plus delta x. So the velocity here, if we can find it, and this is the theta, the same for theta. Now, so the main thing that we need to find here is that basically we need to inverse. So we have theta, and we always need to inverse this. So we have the Jacobian matrix, and we need always to inverse the Jacobian matrix in order to get to our basically inverse kinematics. So we always need to find the Jacobian matrix first, which is not that complicated. And we need to inverse the Jacobian matrix, which is just an inverse of matrix, and then we can multiply it with the change of the position. And the change of position is represented by the path of movement. For example, I have this path, okay? This path, of course, represents the change of the movement. So I want basically to move this robot arm along this path with specific velocity. And this velocity represented by that. So this basically is known. This we can get it by the inverse of the matrix, and then we can get the change of theta. Now, as I said, if we can get the change of theta, we can know it, and we can actually know the change of xt because it represents that. Then we can easily estimate the next x position and the next theta position if we assume that the step that this robot arm is moving at is very small. Because if we are very small, then we can do that, and we can actually, in this case, we need to do very small theta changes. So we start from, let's say, the default position, then we apply the formula and we move with steady steps, of course, to reach the target. Now, the challenge there of the Jacobian matrix is that, first of all, this matrix need to be invertible, right? Of course, not all matrices are invertible. So, for example, if it's not square matrix, then it will be hard to inverse this matrix. Of course, in this case, if it's not square, you need to use what is called pseudo-inverse, which is okay. So you can inverse the matrix with pseudo-inverse, but it's not accurate enough because it's pseudo-inverse. Now, to overcome this problem, there is called the Jacobian iterative model. And the idea of Jacobian iterative model is that I can actually now have multiple iterations where after each iteration or after each inverse of the Jacobian, I now calculate the difference or the cost actually of my model, which is the difference between the target position and the position that this robot arm has reached after the first update, so this update. As I said, because it's for example, in pseudo case, it will not be the same, so there will be some error. So what I need to do now, I need to repeat this iteration again, and until I basically make this, let's say, error as small as possible. So what I mean by that? We have always the target speed, right, which is basically represent the movement along a path. Now this target speed, we can use the inverse of the Jacobian matrix. We can get now the change of theta that I need to apply on the joint to get to move actually the robot arm with this angular velocity, for example. So I apply this angular velocity, which basically would move this robot arm with the hope to reach the target dx. Okay. Now, if I apply the forward kinematic case, so let's say if I take now this delta theta, now multiplied by the forward kinematic or by the Jacobian matrix, not the inverse, but the Jacobian matrix, and this is the forward kinematics, I would get delta x basically, which is estimated delta x, or basically is the output of my pseudo estimation. So if it is perfect, which is basically this inverse is perfect, or it's correct, which is not pseudo, then actually this delta x is equal to that. So basically the difference between them is 0. If it's not perfect, then there will be some error, and what I need to do is repeat this iteration until the dx here and dx here, the difference between them smaller or equal to a defined value. Let's say if I reach an error of 0.5 centimeter or meter or millimeter, depends on the machine, then that would be my threshold. Then I would accept this error and stop. Okay, so this is basically the iterative method. So in general, we have seen toward inverse kinematics the algebraic method, which is the most common for basically most robot arms, the industrial robot arms that you buy. You might get the inverse kinematics model with them already. In cases where we have nonlinearity, in cases where we have kind of path planning or path avoidance, then basically we could use other methods like numerical optimization methods. And in case, of course, we don't know the algebraic model and we need to solve it ourselves, and maybe it's very complicated to solve, then also we can go with numerical optimization methods. Now, numerical optimization method, they are basically has some drawbacks, like they need high computational power, they are slow, and they might end up at not the optimum solution, so they might not be that accurate. Then for that we would need like other methods. Now there's another method, basically black box models, which is neural network or machine learning, but for that we have also drawbacks because we need big data and we have instability. Now the best method, let's say if I want to order them, the top one would be, if you have the algebraic, then go with the algebraic. If you don't have it, then the best thing to follow is the Jacobian as a next. Now Jacobian, the challenge there is the inverse of Jacobian matrix. If the pseudo or actually if the error of the pseudo inverse is really high, then you cannot go with the Jacobian. Then you need, for example, to go with either numerical optimization or neural network. If you have big training data, then maybe neural network would be much better than numerical optimization because it's much faster than doing always optimization and search basically to find the optimum solution. Okay, so for the exam, what is really important to know is, for example, how to apply these three different methods. You don't need to, for example, solve these equations for the algebraic. You just need to know the general algorithm, how it works. For example, you need to just say the steps that, for example, first you need to multiply and then you need to search for the set of questions. And basically, for the other methods, for the Jacobian, it's very easy to know, and basically it's good to understand how it works. So, for example, that you need to get the differentiation of the forward kinematics, and you get then the Jacobian matrix, and then for the inverse you do the inverse of that Jacobian matrix. And it's basically for this one also you need to know it. So in general, in the exam you get a question, and we will give you an example of the exams, by the way, but you would get the question is, let's say, define for me two methods for inverse kinematics, and what are the drawbacks and, for example, advantages of two methods. Now you might get a question about Jacobian method itself to explain it, or you might get a question about the algebraic methods, what are the steps that you need to follow to get to the algebraic solution without doing the solution. You don't need to do that. And maybe, or you need to explain the neural network, or you need to explain the numerical. So thank you very much. In the lab we would have some practical examples about forward and inverse kinematics. But now for the lecture, this was the last session from my part. I hope you enjoyed it. Sorry for the inconvenience because of the online and the delay probably of uploading the lectures because of the change of technology and online and so on. But yeah, I hope you enjoyed. And as I said, if you have any question from now until the end of this semester, just feel free to contact me anytime. Thank you.